Hi, welcome to tutorial 6.3 part 3, the third and final tutorial on the Bohr atom. Okay, in the last two we figured out how we could calculate the energy associated with an electron in a hydrogen atom in different orbits. What we're going to do this time is say, okay, if an electron moves from one of these orbits to another, can we see evidence of that in the lab? And the answer is going to be yes, and it's going to really give us confidence that Bohr is onto something, that there are only certain allowed orbits in some sense of that word in a hydrogen atom, and therefore that atoms have a particular electron structure. So let's have a look at this first one, and then we're going to build up slowly to make sense of the big picture. If you had an electron in the third orbit, and it dropped down to the second orbit, and the energy in question was emitted in the form of a photon, what color of light would we associate with that photon? We can calculate it, and then we can go looking for it in the lab and see if it actually exists. So let's first calculate it. Let's get the energy in the third orbit according to Bohr, get the energy in the second, subtract the two, convert that energy into a particular color of light, and then ask ourselves, do we see that color of light given off when we take a hydrogen atom, excited, that is, give it some energy and allow the electron to drop down to this lower energy? Do we see this kind of light given off in the lab? Like I said, the answer is going to be yes. Let's do the calculation. Number one, we've done this before, straightforward. Negative 13.6 electron volts divided by 2 squared, because we're talking about the second orbit here, leaves us with negative 3.4. If we divide it by 9, that is by 3 squared, the energy associated with the third orbit is negative 1.51. Let's subtract the two. We end up at the second. We started at the third, so we're going to say minus 3.4, what we have at the second, minus what we had in the third, which is a negative 1.51. These two negatives become a positive, and I subtract or add the two numbers, and I have negative 1.89. Yes, it makes sense that it's negative. I'm going to lose energy. I'm going to release that energy when I drop down from the third down to the second. What is that in joules? Minus 3.02 times 10 to the minus 19. Now I have a number that is negative because it was emitted, but I'm going to turn that into a positive number to see how much, what would be the light associated with this particular energy. All right, so let's go and think of this now in terms of the emitted photon that would be given off because of this transition. The energy that we had was 3.02 times 10 to the minus 19. I've made it positive here because I'm talking about the energy now that the photon has. Dividing by Planck's constant, like we've done before, gives us this frequency of light associated with this energy transition. What is this in wavelength? Let's try to get the wavelength for this. We've done this lots of times. Take the speed of light and divide by that frequency. I end up with a wavelength of 6.57 times 10 to the minus 7, or 657 nanometers. Now I'm going to show you on the chart that that's exactly what we see in the lab, minus a small difference because of rounding. So in the lab, what we see when we take hydrogen and heat it up and analyze the light that's given off as the electrons are emerging or moving back down to lower energy levels, we see these 4 bands of color. And one of them happens to be very close to the number that we just calculated. We calculated 657. Here it's 656. Just a small difference in rounding. So that's given us some confidence to say, hey, I kind of know what that band of light is. I know that, or it seems like that is responsible, or where that's coming from, is a transition from the third down to the second orbit. That is when an electron is in the third orbit and drops down to the second. How about these other colors over here? Why these particular colors? And more importantly, why not a whole band, a whole set of colors in here? Well, first, why not a whole set of colors? Why not all the colors of the rainbow as we move more energetic down to less energetic? Would be because only certain energies are allowed in a hydrogen atom. That's already a big deal. If that's substantiated, that at least makes sense of why we see these unique bands of color. All right, let's see if we can calculate this 486 one, and then we're going to look at these two as well in a second. All right, so the next one, how about if we drop from the 4 down to the second? And notice I kind of have drawn this arrow also with a certain color to kind of give us a hint of what kind of color we're looking for. Let's get the energy in the fourth and the second, and then subtract the two from each other. Energy in the second, 13.6 divided by 4 gives us negative 3.4. Energy in the fourth, 13.6 divided by 16, negative 0.85. Again, subtract the two from each other. We drop down to the second, starting from the fourth, so minus 3.4 minus a negative 0.85 leaves us with a negative 2.55. Yeah, that's right, it's negative because we've emitted, we've evolved that much energy, we've given off that much energy in dropping down to the second from the fourth. In joules, it's negative 4.08, but I'm going to turn that into a positive number now to see what kind of photon of light is associated with this kind of energy. That the emitted photon that has 4.08 times 10 to the minus 19 joules, what's its frequency and what is its wavelength? All right, first let's get the frequency. The energy that we just calculated divided by Planck's constant gives us the frequency, 6.16 times 10 to the 14th. And finally, what is the wavelength associated with that? Divide that number into the speed of light. I get 4.87 times 10 to the minus 7. I have a wavelength of 487. I say, wow, it was 486 on the lab data. That's really close. That's looking pretty promising. Looking back at the data, yeah, that looks like this is this transition right here. I think I'm kind of starting to see how this works. This is the transition from the 3 down to the 2. This represents the transition from the 4 down to the 2. I'm guessing, since this is more energetic, this is the 5 down to the 2, and this is maybe the 6 down to the 2. And that's exactly what it is. If you do the calculations, that is from the 5 down to the 2, what do you actually get? There's no reason to go through it all. Just do it yourself. Find out the energy in the fifth, energy in the second, subtract the 2. You get a difference of 2.86 electron volts. Convert those into joules, get the frequency, get the wavelength like before. 434 nanometers is what you end up with, is the kind of light that would be emitted to account for that much energy transition. This is looking promising. There's our 434. The 410 works exactly the same way. If you calculate the energy in the 6 according to the Bohr model and the energy of the second like we've been doing, again the numbers come out. 3.03 electron volts is the difference in energy. Find out what kind of light would be associated with that energy. It turns out to be light that has a wavelength of 410. Well, this is a pretty big thing. So we're saying, look, we're making sense of this is called a line spectrum. Why there are these unique bands of color given off when we heat up some hydrogen atom. We're making sense of something that just wouldn't make sense otherwise. And more importantly, we're making sense of why we don't see all the colors of the rainbow, because we're already used to associating different kinds of light with different energies. We don't see all the different lights, all the different transitions of color. We only see certain unique bands of light, giving us confidence that the electron only exists in certain unique orbits in a hydrogen atom. We're left with a few unanswered questions, though. We say, okay, I'm kind of seeing this. These are all transitions down to the second orbit, but how about the other transitions? What happened to those? How am I supposed to make sense of those? For example, if I do the calculation from the second orbit down to the first, not something down to the second, but down to the first orbit, then what kind of energy do I get? Again, the calculations are like we've done before, so I'm not going to go through them again. But the kind of light that would be given off, in this case, would have a wavelength of 122 nanometers. You say, oh, I get that. Yeah, that is not in the visible range. That's in the ultraviolet range. That would be off to the left on this particular chart, off here someplace, and my eyes can't pick that up. It can be measured, but I can't pick it up with my eyes. So transition down to the first from the second is already ultraviolet, so I can now make sense. I'm going to go back to the picture from before. Any of these other transitions, if the first down to the second is already ultraviolet, certainly the third down to from the second down to the first, all these other transitions down to the first must all be in the ultraviolet because they have even more energy associated with them than the drop from the second to the first. So none of those transitions would be visible. That is, from the sixth, fifth, fourth, third, or second down to the first. All those would be in the UV. How about other transitions that we haven't dealt with? So we made sense of this. It's not visible. It would be down here it would be up here someplace in the ultraviolet. But how about the transitions to places that are not as far as down to the second? That is, for example, from the sixth to the third, and for that matter, any of these other ones. Well, let's do the calculations for the sixth down to the third, see what we get. If we do it out, we get a wavelength of 1,094 nanometers. We say, oh, okay, that is too long a wave to be visible. However, it's in the infrared. It can be measured. We just can't pick it up with our eyes. And the same kind of conclusion that we came to with the last one. We're going to say, look, if the transition, I'm going to go back to see it, if the transition all the way from the 6th down to the 3rd is already in the infrared, any of these lesser transitions down to the 3rd, say from the 4th or the 5th, must also be in the infrared, and therefore not something that we can discern with our eyes. Okay, that's it. What do we have? We have evidence for the Bohr atom. We have evidence from in the lab. We can see, yeah, these various line spectrum make some kind of sense now. It makes sense why there's particular lines and not a continuous spectrum of colors. And so we're moving forward saying, okay, I think our model of the atom is starting to take form. Electrons do have a structure, at least these kind of orbits in the Bohr model right now. And that structure starts to make sense in terms of where electrons are existing in a hydrogen atom.